Okay, part 2 of section 5, where we actually talk about the error when we're computing with the alternating series, okay? So what it says basically is if you take an alternating series, so for example, this one right here, okay? It's equal to, if n is equal to 1, I've got 1 over 3, it looks like, is that right? Yep. And then minus 1 over, if n is 2, we got 5, plus 1 over 7, minus 1 over 9, plus, if you added those terms together, and I'm going to make this really, really, really big, you got this crazy number line. And if we were to run, oh yeah, we already know the alternating series test. If you ran the alternating series test on this, you would quickly find that 1, the lim, as n goes to infinity, of 1 over 2n plus 1 is 0, and 2, a sub n, we can do it this way, is 1 over 2n plus 1, but 1 over 2n plus 1 is a sub n plus 1, and he is a bigger denominator, so he's definitely going to 0, definitely decreasing, and so therefore converges. And that's exciting news because here's the thing I want to show you, as you add the numbers together one after another, so you start at 0, bam, you add the first guy, now you're at 1/3. Then you go, boom, now I'm going to subtract 1/5, etc. There is a limit here. There is definitely a limit because we just showed that it converges, and that limit or sum is in here somewhere. Here's the thing, very simply put, if you decide to approximate this guy, okay, using one of these partial sums, let's say you use the third partial sum. Boom. Okay, so you're going to add 1/7. You added 1/3, and then minus 1/5 and plus 1/7. So you're going to say the sum is approximately the third partial sum, which is equal to 1/3 minus 1/5, and then plus 1/7, whatever that turns out to be. Okay, so the thing is this, you ready? How far off are we with this partial sum? Every time we add, subtract, add, and we're landing right here, this is s sub 3, by the way. The error is this difference between the actual sum and u. Okay? Well, we don't know what that is. If we knew what that was, we would know what the sum was and we'd walk away. But here's what we do know, is that for a convergent alternating series, if you add the next term, which would be the minus 1/9, you would land here. But so what? This term's distance here is actually bigger than the actual error that you're dealing with. So what this is saying is that if, as it says up here at the top, if you took the actual sum and subtracted s sub 3 from it in this example, then your error, this is your error, how far are you from the actual sum, is less than the very next term, which would be the magnitude of it. I would say it's less than 1/9, which is a sub 4. Okay, so we're within 1/9 of the actual sum is what this error estimate is saying. Okay, isn't that bizarre? It's like, oh, all I have to do is add up 50 terms, and then the 51st term would be an upper bound on our error. That's it. Let me write that in English. If we add 50 terms, so what we're looking at is s sub 50, right? We will be, well, I'll tell you what, we will be within a sub 51 of the, and I'll put absolute value around them, of the actual sum. So the more terms you add, the closer you get. But it's interesting because this problem up here is going to say, find an upper bound for the error if we add the first 50 terms. So I'll do problem 1, or whatever it's numbered. I'll say, okay, so we have a series, minus 1, and its n is equal to 0 to infinity, and we got n, or something like that, and, okay, n minus 1, and this is 1, okay, and downstairs we have 2n plus 1. Okay, so if we estimate the error, we go, okay, so the sum, or S, minus S50, remember the problem is saying, what's an upper bound for the error if we go out 50 terms, is going to be less than the absolute value of the 51st term, which is the absolute value of, I don't care, I'm just going to say, I'm going to ignore the negative, I'm just going to simply go 1 over 2 times 50 plus 1, which turns out to be, the 51st term, sorry, the very next term, okay, which turns out to be 1 over 103, which is, 0.97 roughly. Okay, so that means we are within 0.97 if we, of the sum, the actual sum, if we add up the first 50 terms. That's not too impressive, 0.97. You're almost like a full unit away from the sum. This guy, it bounces back and forth quite a bit. He has all the time in the world. The second question it asks, how many terms will it take for our error to be less than 0.0001? Which, by the way, if you turn it into a fraction, is like 1 out of, what, 10,000, I think? Okay. So what we do is we just say the following. Okay, suppose, so our error, sum, minus S sub n, let's say, because we don't know how far to go to get that error, well, we know it's going to be less than the absolute value of the n plus first term. Okay, and now here, which is equal to, I'll just do this, I'll go 1 over 2 times n plus 1, not 50, but n plus 1 this time, plus 1, which is equal to 1 over 2n plus 3. And here's the thing. We want our error, we're going to force it less than 0.00001, which is the same thing as 1 over like 10,000. Now the reason I write that is because that's an inequality. It's 1 over 2n plus 3 must be less than 1 over 10,000. What I like to do is cross multiply, so 10,000 is less than 2n plus 3. So 9997, subtracting 3 is less than 2n. So that means that n needs to be greater than 9997 over 2, which is, I think, something like, what the heck is that guy? Roughly 4,999 terms. Oh, goodness. Well, that's pretty interesting. You would actually have to add nearly 5,000 terms to get your error that small. So this is a really slow converging alternating series. But isn't that interesting? The part that you really want to digest is this leaping, whatever you want to call it, a cricket or whatever, each term you add. So this example here, kind of understand that. And then when you're ready for the, figuring out how many terms, then it gets a little more abstract, but it's this guy right here. What I have for the tail end of this section is I have a messed up set of problems, remember? First of all, this should be 1, this should be 1. And secondly, it goes find an upper bound of the error for these other guys, and how many terms would you need? Okay, so if I answer that on all three of them, the upper bound would be, well, the 51st term, the magnitude of the 51st term. I'll write it in English, 51st term. That's for all, in this case, I'll just go, well, A51. Okay, equals. So that would be an upper bound for our estimate, and over here, same thing, A51. Since we're going for the first 50 terms, what's the error? Well, in this case, it would be equal to 1 over square root of 51 plus 1, or 1 over the square root of 52. Whip out the calculator. What do I get there? Let's see. So 1 divided by the square root of 52, okay, is about 0.13. Did I do that right? That doesn't seem right. Okay, so we've got 0.138. 0.138. I'm not sure I did that right. Okay, what about this guy? Was that error okay here? Yeah, that was 103. I divided by something small. Let me try that again. 1 divided by 103 is, oh, that was a mistake. Okay, so this guy actually is 0.0097. Do you see how I recognize an error? And we figured that one out, 0 point that. Okay, well that's not bad. That's not a bad error now that I look at it. So we are within 0.0097. I wish I'd done that right to begin with. Well, you know, it's kind of free form here. So this guy's error is not so good. He's actually going even slower. How about this one? I ignore the cosine. I just simply go, what is 51 divided by 2 to the 51? You're going to like this one. So 51 divided by 2 to the 51 is really small. It's 2.26 times 10 to the 14th. It's 10 to the negative 14th. So it's 2.26 times 10 to the negative 14th. So that's like 0.000005, 6, 7, 8, 9, 10, 11, 12, 13. I think it goes like this. 226. So that's really good. Okay. And the last one would be, well, it's 1/3 to the 51 over 51. Or I might make it easier and go, it's 1 over 51 times 3 to the 51. I think you're going to find that this is even smaller, super small. So what you get is a feel for, you know, depends on the series, the terms themselves. They go to 0 very quickly or not, depending on how it's been defined. How many terms would you have to add in order to have the error less than 0.0001? Well, I ran this one. What I did is I went, well, it would be 1 over square root of, what is it? What was the form? Oh, yeah, 51, the 51st term plus 1, and I would see where that was greater than, or less than, I should say. We want that less than 0.00001. And I did that one, and I think I came up with a crazy huge number of like about 90 million. So n is equal to 90, is it 90? 99. 99,999 and 1,998. So terms. You really would have to add a lot of terms because of the square root. On the second one, I think I finally got like n is equal to, n is equal to 21 terms to get that happening. And on this last one, I was goofing around. This is the last thing I'll mention. Two things at once. We'll say, what's the error? Okay, let's look at this last one, which I'm writing as series. It starts off as negative 1/3 to the n over n, which when you start writing out terms, let's say we start at 1, remember, to infinity, you've got minus 1/3, then you got plus, and in this case it's going to be 1 over 2 times 3 squared minus 1 over 3 times 3 cubed plus 1 over 4 times 3 to the 4th, and you keep going. Now what I did in this case is I went kind of term by term to figure this out. Look at how far I have to go. 1 over 5 times 3 to the 5th plus 1 over 6 times 3 to the 6th minus 1 over 7 times 3 to the 7th plus 1 over 8 times 3 to the 8th, and finally minus 1 over 9 times 3 to the 9. What did I do? I took my calculator and I went term by term by term, and this is the first one. This guy right here is the first one that's less than 0.0. It was actually, I'll give you the number. It ended up being, when you compute this one term, it's equal to 0.12345 and a 5, which is less than 0.00001. So that's the first thing that works. Okay, so that means the sum ahead of it. 1, 2, 3, 4, 5, 6, 7, 8. So this is S sub 8, and this guy is A sub 9. Okay. This is the part that's tricky for students is, okay, I found the first term that's less than that. Therefore, my estimate is all these guys ahead of it. All of them. That's 8 terms. Okay. I won't bore you with the details. I actually did compute this one. What I got was a negative 0.26286. Oh boy. Negative 0.286767. Couple more 7s, 28, 7728, and it keeps going. And here's the thing. It's accurate to within 1, 2, 3, 4, maybe even 5 terms. Very accurate. How do I know that? Well, another lecture we'll talk about it. But I can tell by looking at the numbers here that the first 5 terms, in fact, are accurate as far as the sum is concerned. So that's the story. We're going to see it again and again, the alternating series estimate theorem. Basically, if you add 20 terms, you're within the 21st term of the sum. Okay, and you pick any number you want, and that's how it works. Okay, that's enough to maybe play around with. We'll see you at the next one.